Viitorul e al tău, noi punem temelia. Construim pentru România. Universitatea de Construcții București.
Thank you very much. Too much respect to me. Probably I don't deserve it, but anyway. Thank you, the Romanian Geotechnical Earthquake Engineering, the Greek Society, in particular the President and the General Secretary and Loretta and Radu and too many good friends here for this invitation. You have seen something that we, the engineers, are facing all the time, how we change it.
Arrow down.
Down?
Yeah.
Okay. What you have seen here is the struggle to anticipate uncertainties. Uncertainties is our life, everyday life, and we must know that our world is a probabilistic world. So with our modest capacities and knowledge, we try to solve this problem. Some people here from the engineering society don't like at all the probabilistic approach, but it is a probabilistic world, my friend George. We cannot avoid it. And we try to solve it as much as we can, not always in a successful way, and you have seen too many numbers there. It is an effort to give some answers to this probabilistic problem that we have to face every day. And you will see something more here in my presentation. It will not be so detailed. There will be a lot of maps. I will try to somehow give a fundamental, not a fundamental, an implicit answer to what Radu said about the future of the geotechnical society and engineering and whatever, which probably is facing some problems not only in Delft but everywhere. And I will try somehow to make a bridge between geotechnical, structural, risk assessment, society, etc. And probably it will be a kind of solution to the question that you raised, that the geotechnical engineering is not so well seen in the future. I'm not sure, and probably you will see something. Now, I will make a short presentation of the definition of seismic actions in Eurocode 8. But then, as I already said from my introduction, I will try to go further. And what is this? Going to the seismic zonation, the seismic hazard, the seismic actions for the engineers through the Eurocode to the national annexes that we have to produce. So the seismic zonation, it's very important. But then I will not stop there. I will try to show somehow with the example in Greece how all this will go a little bit further for the risk assessment, because finally all the decisions are based on this risk assessment that we have to do. Okay, a lot of help from my colleagues, Anastasiadis, Eviriga, and Apostolaki, so a lot of respect to their work, and many others. First thing first, the definition of the seismic actions. The Eurocode made some basic, let's say, new developments. Is the consequence classes. We have seen a lot of this, and probably we have to discuss how the consequence classes are combined. It's not so obvious. Then it is evident that the NDPs are on the table, and we have to see how it will be compatible across Europe. Limit states, and we say at the end that for new structures, it is required that at least the non-exceedance of the SD limit states has to be verified. For new structures, the big problem for the risk assessment in Europe, and not only in Europe, is for the existing structures, which a lot of them, as you will see later on, have been designed with no code. And the risk is there. And on the right side, you can see the maps that we will discuss later on that have been produced recently for the whole Europe, and they will affect whatever we are speaking about today. So what are the basic new things in Eurocode 8? The first is that we skip the PGA, the acceleration, the peak ground acceleration at 0 period. And we are proposing two values, S alpha and S beta, for low periods and intermediate period, 0.3 seconds and 1 second. Is the first major thing. The second major thing is that we define the hazard for so-called bedrock or outcrop or whatever, but rock conditions, and for 475 years return period. And this is different if we take into consideration the consequence classes and the limit states. And above these values, we apply the amplification factors, F alpha and F beta, which are intensity and soil dependent. This is a major new thing in Eurocode 8, which will affect everything. Of course, all these are NDPs. We say NDPs not because we want to skip the problem, but to give the freedom to each country to adapt the basic idea. And the basic idea is S alpha and S beta and 475 years. I know that in Romania you do not have the 475 years, it is the 200, but you have to respect the 475 and see why you are proposing this. But anyway, it is something that it will be very interesting to be discussed. The seismic actions are defined by this simple formula. We have the F alpha, which is the amplification factor. Ft is the topographic amplification factor. I will not speak a lot about this. The spectral value S alpha, which is for the low periods, as I said before. And there is a coefficient delta, which depending on the consequences classes, which should be also NDP. This delta may get different values. The normal one for ordinary buildings is 1, but you can have for other buildings from 0.6 to 1.6. 1.6, for example, or 1.25 is for tunnels. Some important industrial facilities, some petrochemical, etc., may be 1.6. This means that we increase the loads by these values. We believe in these values? I don't know, but it is something, I would say, reasonable estimation. Okay, then the consequence classes is very important, the seismic actions as well, and there is something that we say that in case of important structures, and despite the NDB values, which are given in each country, EC8 suggests the performance of site-specific seismic hazard analysis. This was, again, something very important. It means that if you have an important structure, an important facility, you cannot just say, I have the NDP and this is this value. You have to perform site-specific seismic hazard analysis with everything that you have probably seen in the previous presentation. It can be done either in a deterministic or in a probabilistic way, but it is a site-specific seismic hazard analysis. Okay, we said that we are working with the 475 years return period. Okay, but we know from the previous codes the importance factor, for example. This importance factor is not existing anymore. We have the consequences. And we have these words, these capitals, NCSD, DL, which means the non-collapse, for example. I'm designing something for non-collapse. Or I'm designed for the damage limitation. It is something that you have to be little by little more familiar with what is missing, and in the Eurocode there are some explanations about this. And then we have the consequent classes. So if I want to design a tunnel, for example, which is the CC3A, and for non-collapse, because I believe that it is very important for many reasons, etc., I am giving an extra amplification factor, which is the gamma, as you can see, and it is 1.8. And this is for other industrial facilities, important facilities, etc., etc. Are these values 1.8, 1 and 25, and 0.6 are, let's say, correct? I would say I'm not so sure. We have recently made a publication in BE, and we made an analytical estimation throughout Europe of these values, and we found that in some North European countries, for industrial facilities, we reached, for the non-collapse, not the 1.8, but numbers like 2 and 3. And this is very important for the German industry, for example, because, okay, 1.8, it has been estimated somehow, but if with the methods that we will see later on, we may have these values of 2 or 3, everything will change, as you understand. And the German industries in across, let's say, the border with Switzerland or with let's say, with France, will not be so happy. Anyway, these are values that are proposed, but does not mean that they are 100% accurate. And then we have this famous spectrum, NDP values for the SA and the SVITA. And now something which is important for let's say, this specific area of Europe in Romania. The K factor, which is 4, it is the ratio between the two corner periods, which is defining actually the length of the plateau. I believe that this is not accurate for Romania. This K factor with 4 gives a plateau which is going up to 0.5. I believe that in Bucharest it cannot be applied. It should be at least this K factor, instead of 4, it should be maybe 7. But it is up to you to make it. And this is one of the most important issues, I believe, that you have to see when you will make your national annexes to be in accordance with EC8. And how we estimate the S-beta, if we know S-alpha, it will not be in very much detail about this. It is quite explicitly, let's say, set and defined. So you can see how it is done anyway. And now I'm going to something that I am very, very fond of, the site classification. I have participated in this committee. A lot of discussions. And finally, a lot of compromises. Am I 100% satisfied and happy? Honestly, I'm not. But you know, if you are in a committee of Eurocode, etc., you have to make a lot of compromises. Okay, this is the way that it has been voted. So we cannot skip it. It is as it is. The whole thing is that we define the site categories based on H800, which means the depth to a certain layer where we have 800 meters per second for the VS velocity. I know that there are a lot of ways to estimate this with a lot of uncertainties and with a lot of errors. And then we define in this length, in this depth, the average VS value. And with this is the classification, the first part of the classification, with 3 categories of soils, the stiff, the medium, and the soft, and some representative values or ranges of values. And we say, okay, is it possible to make it in every site? The question is probably not. And where I was really fighting a lot within this committee is to introduce a new factor, which I'm believing that it is very important, is the fundamental period of the site, which is something that can be done with an instrument of less than 1,000 euros. So it is something that all the consulting companies can afford. And it is a new parameter which is very important, in my opinion, for the site classification, for the application of EC8 for the seismic actions. There are some tables informative how to define all this. I will skip it. You can see it. And this is what has been proposed in the annex. If we cannot be sure what we have done before with this simplified table that we have seen, and we would like to introduce the fundamental frequency or the period, this is the values that are proposed. Again, there are values which could be respected or not, but we have to put something. So these are the values that are proposed in Eurocode for the fundamental, here is for the frequency or for the period, and the classification according to this. The next big issue is this one. It has been decided in the committee that we don't like the way that NEHARP and the American ways and the American people are proposing for the site amplification factors, which is something, let's say, scale for the different PGAs or for the different spectral values. And we want something which is going without this scaling. So we are proposed this part of the table, it's not so visible, okay, here, where we're supposed to have the capability to make it, let's say, linear without the scaling. The problem here is that the simple engineer has to have a good knowledge of the H800, and this is not obvious. So we propose the default values where we don't know exactly these values. And you can see how we estimate the F alpha and the F beta. And FT, which is there, don't take for the, let's say, in consideration for the moment because it is an extra amplification for the topography effects. We had some discussion about the basin effects, but we said that, and we work a lot on this in Thessaloniki, but we said that it is not so mature, so basin effects are not included, and we left it for the next generation of the Eurocodes. And for the topographic effects, we just took what is already existing, and we put it again without a lot of a consideration on that. So I am not so sure that this can be easily applied by an ordinary geotechnical or civil engineer. So this is why you will see in a couple of figures later what we are proposing for the national annex in Greece. Of course, we have the peak ground displacement expressions and the peak ground velocity as well. And again, you can see that the information that the ordinary engineer has to have in order to apply this, it's quite beyond what probably in a small village someone can afford having it. Anyway, the vertical acceleration. We are proposing these expressions. The basic idea is that the 65 or 70% that we had before is not existing anymore. It is variable, as you can see, and in some cases it can be as high as 80% of the horizontal acceleration. And there are several other clauses which are dealing with different aspects about when and how we make the site-specific ground response analysis, spatial variability of the ground motion, which is very important for long structures, bridges, and tunnels, the fault proximity and crossing, a lot of discussions with George, how we anticipate this issue. Very important. It's not so simple as it seems. Anyway, you will see how to select the time histories, because more and more in big projects we make, let's say, the so-called full dynamic analysis. So we need to have time histories, the topographic amplification, and finally the reduced elastic spectrum for the force-based approach, which is based on this simple equation, which takes into account the overstrength and the deformation capacity and energy dissipation capacity. Now, we worked a lot on this issue, and we believe that it is not easy to apply. So we are proposing a new site classification. It started almost 10 years ago, and it developed through the years. The basic idea is that we have to introduce a fundamental period, one. And then we cannot skip in the classification what we already know about the SOIT categories, SPT values, PI, undrained shear strength, and whatever. So we have to merge it. This is a simplified schema where you can see the different categories, A, B, C, D, E at the end. But if we introduce the fundamental frequency or period, we are forced to subdivide some classes, in particular the class C of the Eurocode. So we have C1, C2, and C3. And this is a table very similar to what we know already from the American code or from the European code, but we introduce the third line, which is the fundamental frequency, and a quite detailed description of the soils, B1 and B2. This is, okay, we say we have the rock, we know it, but we have the very stiff soil, and in our opinion, it depends on the depth of this. If it is quite shallow, less than 30 meters, or more deep, down to 60 meters, it's not the same, because the fundamental period will be different. And so on and so forth. We are proposing this table, and then we go to this simple table with the amplification factors. For the low period, 0.3 seconds, and for the intermediate one in 1 second. S alpha, SS, as you can see, you can divide by 2.5 to find out the PGA if you want to work with the PGA. In our opinion, and in between, you can make an easy interpolation. This is very similar as a structure to NEHARP, to the American code, and we believe that it is much simpler to be applied. So our idea is that we have proposed this in the national entities in Greece, and I suppose that there will be a discussion in the next couple of years if we will apply the previous one as national annex NDP or if we will go to this simple. And just to tell you that all this has been based on more than 3,000 or 4,000 cross-hole and downhole data all over the world, mainly from Europe, from the United States, and from Japan. So all the statistics that are behind this are based on not on 100 records that we had, and George knows very well in the previous, but more than 4,000 records with very well-known site conditions all over the world. Probably we can improve it, but the whole idea, as you can see, is different. Okay, this is about the first part, which is the site conditions and the seismic actions. Okay, but an engineer is using a code and needs a hazard map, as we say. And here is another big issue. These are the two main publications of ours, because based on the developments of Eurocode 8 on one hand, and on the other hand, the new developments through few very recent European research projects, which have been funded exactly for Eurocode 8, to help Eurocode 8, we are going to propose, and we have proposed, the new seismic zonation of Greece. And it is said explicitly in Eurocode that you can make your own NDP for the hazard, but you have to account what has been done in the project SHARE and SERA, which is the European seismic hazard model with the number of 20 behind. You have to account this. And what is this? Is these two maps for the SA and the S-Vita. And you can see that in Romania and in Francia, you have a very, very, very strong numbers. Okay, the problem is that in order to apply the SHM20, we have to have some input databases. The European pre-instrumental earthquake, which is again made from scratch from the beginning. This is the first map. This is for the instrumental European database. Now we have about 60,000 events around Europe. And the most important thing is that there is an homogenization of the way that we're treating. I'm saying this in a very simple way. If I am in Greece here and in Bulgaria here, in my 2 feet, we might have a different seismic action. Now, this with the SHM20 has been solved. It is all together now. And it is an homogeneous methodology in order to do this. And the third database that we need is the fault sources. Again, a lot of people worked here. You can see the publications. All this is one of your people here in Romania, is Laurențiu Danciu, who worked a lot. And he has done with many, many others, but he's one of the key persons of these developments. And you can find everything in this FR database. Okay, let's go to more details. How we define the S alpha and S beta. For the S beta, we go to the 1 second, okay? Because all the results of the SHM20 is with the uniform hazard spectrum. So we have to have a methodology in order to come up with the S beta and the S alpha. And you can see here how we define the S alpha and the S beta. It is well known and accepted. And the SHM20 gives hazard maps with different, now is the probability, now is the uncertainties with different percentiles. We have to do it, otherwise it is not possible. And the problem with Romania is that it's not belonging to the standard source models. It is the non-subductive deep seismicity sources, so you have a lot of work here. I'm sure that you have already done because you are not, let's say, as in Greece or in Italy with area sources and active faults. It is a rather peculiar situation, and I'm sure that you are working on that in a very thorough way. Now, with this short introduction, we go directly to what we have done in Greece. This is the seismic hazard that we have. This is the area sources. This is the active faults. And we apply this methodology, the unified and homogeneous methodology. S alpha and S beta. The big problem here is we have the grid and we have to go to the zones, which is not obvious because we cannot go to the grid, because in some cases we may have in one city the difference of the order of 2 or 3 of the seismic action. So we have to go with zones. And we applied a very well-known methodology in order to go from the grid, from the points to the zone. And we have also seen if taking into account the seismicity in the sea area or around Greece will affect the whole thing. Is not affecting, so we remain with what is seen in the left side. And the natural breaks, Jenks 67 as methodology, the statistical algorithm is used. And we have started with 3 zones. And then we try to see what is giving with these differences here. And what we see here, it's more clear in this figure, that in some places we have negative values, which meaning that the zonation underestimates the PGA, which is, let's say, produced by the grid. And the positive ratio means that we have overestimation of the PGA. So we spent a lot of time thinking how we will solve this problem, because we want somehow to be realistic and see what is the most interesting. And we introduce an extra table, which is this one. We said as engineers and practical people, we say that if we have important cities like Athens or Thessaloniki with a lot of people living there, we are not allowed to have big differences between the points and the zones. So we allow there the difference to be up to 10%. But if we have a small village, we can go up to 20%, because the population living there are not so important, the other activities are not so important, etc. So with this one, we start working with different examples, and we use as these 63 big cities in Greece in order to be able to do this. And little by little, we went from the 3 zones to the 5 zones that we can see at the end, where we somehow satisfied the criteria that were defined before based on the population, which is affected by our decisions about the seismic actions. And this is the final map, and this is the final values for the 5 zones, S alpha, S beta, the PGA, and the periods in order to define the spectrum. It's different from the actual seismic zonation, and you will see later on the difference. And as we have the amplification factors already defined, we may use this one with the amplification factors included in our zonation, because the tables that we can see are with the amplification factors for each, let's say, PGA that is representing each of the zones that we can see. Of course, we try to be as good as possible regarding the administration limits, because you cannot have an administration limit, a small one, where half of this is in one zone and in the other. So there is some kind of smoothing, which maybe will be further made later on. Okay, this is the idea so far, and we go the next 9 minutes, as I see here, how all this is affecting the risk. The first important thing is the exposure. In Greece, based on the census of 2011, we have about 3,200,000 residential buildings. We are dealing here with the residential buildings, not with the others. And you can see the distribution around. The municipality of Athens has 50,000, and the municipality of Thessaloniki, not the agglomeration of Athens, neither of Thessaloniki, and in Thessaloniki is about 20,000. The second important thing for the exposure is what kind of buildings, of structures we have. In Greece, almost the 70% is reinforced concrete, and the rest is masonry. This is probably the most important. The red one means that these structures have been without any seismic code, which is about 40%. Low code is another, let's say, 30%. And with the high code, the recent codes of the last 10 or 20 years is not more than 15 or 20%. This is very important if you want to make the risk. Sorry. And how high are our buildings? Most of our buildings, if we take the whole Greece, is not more than 1 floor, and very few, only, let's say 5% is more than 6 floors. Another important issue, how cost is to estimate the replacement. Because everything that you will see later on is based on the replacement cost, how much it costs to make the retrofitting against the full replacement of the structure. And we estimated these values, 1,500 euros for Athens and Thessaloniki, and for the rest of Greece, only to, let's say only, not only, a little bit lower, the 12,000 for the replacement. This means that the total replacement cost is about 1,200 billion euros if we want to replace everything, just to have some figures. We go for the seismic hazard, and our basic idea is to compare what we had with the present Greek code, with the present Euro code, and with the new code that we are proposing for the seismic hazard, and see the comparisons. This is the present code in Greece to the left side, which is used also for the Eurocode, as you know. The main difference between these two cases is that the Greek code has no amplification factor, the 2000, and the Eurocode, as we say, is the same zonation, but we apply extra amplification factors. I'm sure that George will laugh with this because it is something that, let's say, happened without anybody asking us. You know very well. Nobody asked us if it is correct or not. We just took the values that we had with no amplification factor and they applied the amplification factors for the soils A, B, C of Eurocode. Something which is absurd anyway. And to the right side is the new zonation. How we make a geotechnical zonation in large scale. Here, Loretta, it's the big problem if you go to the large scale. What you have very well presented is for a single structure where I'm going to define. But what happens if I want to make something for the whole Romania or for the whole Greece? There is one method, I'm not very sure that it is very correct, George as well, we have discussed a lot about this, is the Wald and Allen method, which is based on the slope. More or less they say, if it is very steep, the Vs velocity will be high. If it is not very steep, it is okay, but you may have a flat with a rock side. So we have to combine with geology, and in Europe we try to merge these two things. Bergem is working also on this quite a lot. And you can see to the right side the VS model that we produce from the slope plus the geology plus the verification in some places where we have detailed macrozonation studies. So it is a combination of different issues. And this is the site classification based on the categories A, B, C in order to apply the amplification factors. And now you have the present Greek code before this extra amplification from the Eurocode 8 for the PGA, the 0.3 second, the 0.6 and the 1 second. This is when we use the Eurocode 8, and this is where we are using the new zonation. Some values. I'm skipping all this. For that, we need the fragility curves, and to use the fragility curves and the vulnerability curves, we need to make the classification of the different typology of the buildings. And we used this, which is also used in GEM, that you know. Probably there are some differences with the synergy approach or with other approach, but anyway, it's something that can be global, so we use this classification. And this is the vulnerability curves, as we say. What is the vulnerability curve? In this axis, in the vertical axis is the degree of losses from 0 to 1. And in the other is the intensity. The intensity, depending on the typology of the building, may be expressed with the PGA or with a spectral value. And this is for the different classifications that we are using. Let's go to the results. The number of buildings that we have with the 3 different examples that we have seen, EAC, Eurocode 8, and the new zonation. The percentages of the buildings are shown in this pies and with the numbers below. The percentage of buildings with extensive to complete damages in Athens is 1.5%, in Thessaloniki 1.6%, and you can see how it is distributed across the whole Greece. I'm going to the second scenario, EC8, and to the third scenario. You can see that the percentage of buildings in extensive or complete damage is not changing a lot, from 1 point something to 2 point something, but it's something affordable, in my opinion. Economic losses. This is probably the most interesting. With the scenario of 475 years, we climb up from the 73 billion euros to 100 billion euros. So the government, the state, or the official have to use these values in order to say, okay, I'm satisfied or I'm not satisfied. And, we can go in each city if you want, or in each district. And you can there are a lot of maps like this with the different scenarios. And with this, I believe that I try to give an overview starting from Eurocode 8, the part 1, which is the definition of seismic actions. Already made some comments how much we believe in this or not. I believe that this is very important for the discussion in view of the national annexes. Then we went to the seismic zonation, because in order to apply the seismic actions in Eurocode, it will be through the codes, so we cannot skip making a zonation. It's something that we have to do. And then we have to see how this is affecting the risk. I know that the risk is not based on money, we all know, but it is a simple way to estimate if it goes well or wrong, or it is excessive or not excessive, and how far we can go. So you have seen the whole, let's say, way of thinking from the definition of the seismic actions to the risk. And now it is the committees, the administration, the governments, the European Union, etc., which will take the final decisions if we are satisfied or not. We will never be satisfied. This is for sure. And the uncertainties will be always there. For example, the fragility and the vulnerability curves that you have seen, there is a huge discussion, and Radu knows very well about this, a huge discussion how correct they are. They are not, let's say, either non-correct or correct. It is an estimation. And some buildings here, some magnificent buildings here, are not belonging in any of these categories. So you have to make your own for these wonderful buildings here of the last century. So a lot of things that has to be done in the future. But this is the whole thing. And thank you very much again for everything.
Viitorul e al tău, noi punem temelia.